Today we're going to be talking about complex numbers. What is a complex number? So as you know, there are different sets of different types of numbers, like natural numbers, whole numbers, integers, and real numbers. And there are more sets, but I'm just going to go over the main ones, these four. And as you know, natural numbers are the smallest set. Whole numbers are natural numbers including zero. Integers include negative numbers. Real numbers include irrational numbers, decimals, everything. Now, what is a complex number? A complex number is the superset of all of these sets. Now, you may be wondering, how is a complex number bigger in any way than a real number, or contains more amount of numbers in its set? So you may think real numbers hold everything, but that's simply not true, because complex numbers add in imaginary quantities. Now, you may wonder, what is an imaginary quantity? Have you ever tried to solve this equation? X squared plus 1 equals 0. So, very bad too. So, trying to solve this, you get x squared equals negative 1, and x equals plus or minus the square root of negative 1. Now, what is the square root of negative 1? Positive 1 times positive 1 is still positive 1, and negative 1 times negative 1 is still positive 1. So what is the square root of negative 1? And this is an imaginary quantity. This is imaginary. Now you may be trying different ways to solve for the square root of negative 1. And you may say that the square root of AB equals the square root of A times the square root of B. And as you can see, this still doesn't work, because the square root of negative 1 equals the square root of 1 times the square root of negative 1. This is still 1, and this is still the square root of negative 1. And this square root of negative 1 has been given a name I, or better known iota. So this is your imaginary number, I. And there are different ways to represent complex numbers. And we're going to be learning about powers of I. Like, I is the square root of negative 1. So what is I squared? What is I squared equal to? So we know that I is the square root of negative 1. So if you square the square root of negative 1, you should get negative 1, and that is your answer. But some people may have an argument saying, if the square root of A times B equals the square root of A times the square root of B, then the square root of negative 1 times the square root of negative 1 should be equal to the square root of negative 1 times negative 1, which is positive 1. So I squared should be equal to 1. And the reason this isn't true is because AB, so A times B, or AB, have to be opposite signs, or both of them have to be positive. This rule doesn't work for complex numbers. This identity is for real numbers. And as you can see, we are dealing with complex numbers. And another way to prove this wrong is, we got x equals plus or minus the square root of negative 1 from this equation. So by algebra, the square root of negative 1 squared plus 1 has to be equal to 0, which means the square root of negative 1 squared has to be equal to negative 1. Now, we're going to be learning about more powers of I. We know that I equals the square root of negative 1. And we know I squared equals negative 1. What is I cubed? I cubed is I squared times I, which is negative 1 times I. And that's negative I. And what is I to the power of 4? This is I squared times I squared. And this is negative 1 times negative 1, which is still positive 1. So, you're going to see a pattern repeating. And you can see this is I. And then you're going to get minus 1, and then negative I, and then 1. So you can see it follows a pattern. I, negative 1, negative I, and then 1. And this pattern repeats up to infinity, I power infinity, or at least when it tends to infinity. So, all that we know is that I to the power of 4 times n, where n belongs to an integer, is equal to 1. So any multiple of 4, like I to the power of 400, that is just I to the power of 4 times 100. And this is going to be equal to 1. Because I to the power of 4 is 1. 1 to the power of 100 is still 1. So what can we say with this? We can say that I to the power of 4n plus r equals I to the power of r. Or you could say that I to the power of 4n plus 1 equals I to the power of 1. And I to the power of 4n plus 2 equals I squared, or negative 1. And then you could say I to the power of 4n plus 3 equals negative I. And I to the power of 4n plus 4 equals 1. Or I to the power of 4n is also equal to 1. You can choose either one. Now, how do you represent a complex number? A complex number is denoted by z, and this is equal to a plus bi, where a and b belong to real numbers. And this a right here is denoted by real part of z. And b is denoted by imaginary part of z. And the reason for this is, you can see this is multiplying with I, which makes it an imaginary quantity. And a is a real number, so it's going to be the real part of z. So if I gave you a complex number, 2 plus 3i, what is the real part and imaginary? You're free to pause the video and tell me the answer. So the real part of z is equal to 2, and the imaginary part is equal to 3. So this is how real and imaginary parts of complex numbers essentially works. Now, we're going to be talking about algebra of complex numbers. If you have two complex numbers, how do you add them, subtract them, multiply them, and divide them? Let's denote our first complex number by z1. A1 plus BI1, B1I. And your second complex number, Z2, equals A2 plus B2I. Now, when you add two complex numbers, the real part adds with the real part, and the imaginary part adds with the imaginary part. So Z1 plus Z2 should be equal to A1 plus A2 plus B1 plus B2I. And as you can see, this is the new real quantity of Z, and this is the new imaginary part of Z. How do you subtract complex numbers? If you wanted to do Z1 minus Z2, it's the same logic. You get A1 minus A2 plus B1 minus B2. You add the imaginary and real parts separately. Now, what is the complex closure law? This states that Z1 plus Z2 is a complex number for all complex numbers Z1 and Z2. What does that mean? Z1 is Z1 belongs to complex numbers, and Z2 also belongs to complex numbers. This means that Z1 plus or minus Z2 also belongs to complex numbers. And the reason for this is pretty obvious. I mean, if you have two, because everything essentially belongs to a complex number. But if you have two complex numbers and let's say you add or subtract them, and let's say your I gets removed, like not your real I, but like iota. So, even if it does get removed, and let's say you get a real quantity 5, 5 still belongs to a complex, the set of all complex numbers, because 5 belongs to real numbers, and real numbers belong to complex numbers. So you still get. What is the commutative law of complex numbers? If you add Z1 to Z2, that's the same as adding Z2 to Z1. Which means it doesn't really matter in which order you add complex numbers. It's still going to be the same. What is the associative law of complex numbers? If you add Z1 plus Z2 first, and then you add Z3, so let me remove this bracket, Z3, this is the same as adding Z1 to Z2 and Z3, where we're adding Z3 and Z2 first. And what is the additive inverse or additive identity of a complex number? Let's say you have Z. What do you add to Z for it to become Z? And that's simple, 0. So the additive identity of a complex number is 0, because we add 0 to get the same complex number back. What is the additive inverse of a complex number? What do we add to Z to make it equal 0? We add negative Z, because Z minus Z equals 0. Which, let's say this is Z, so both of them are Z. Let's say Z1 equals Z2, and this is Z1, Z2. And that would mean A minus A, because both of the real quantities and complex quantities have to be equal if these two are equal. A minus A plus B minus B times I. As you can see, this is 0 and this is 0. 0 plus 0I is equal to 0. So, the additive inverse of a complex number is negative Z. Now, how do you multiply two complex numbers? let's say you have let's say you have x plus iy and u plus iv. Now, how do you multiply them? You would multiply them the same way as any old real number. You get xu plus xiv plus iyu plus I squared yv. You just expand the bracket and you get xu plus xiv plus iyu, and this is -1, so minus yv. So xu minus yv plus xiv plus iyu. And you can see we can factor out an I here. So you get xu minus yv plus I times xv plus uy. So you could remember this formula for when you're multiplying two complex numbers, but that's really not necessary because you can just multiply. Now we're going to be talking about associative and commutative laws of multiplication of complex numbers. So z1 times z2 is still equal to z2 times z1. So it doesn't matter in which order you multiply complex numbers. An associative law, z1 times z2, and then you multiply z3 later, is still equal to z1 times z2 times z3, where you multiply these first. Now, what is the multiplicative identity of a complex number? What do you multiply to z to make it z? That's 1. So the multiplicative identity is equal to 1. Now, what is the multiplicative inverse? What does that mean? What do you multiply? What do you multiply with z1 to make it equal to 1? Let's let this equal to x. So z1 times x equals 1. And solve for x. X equals 1 over z1. Which means if you multiply z1 with 1 over z1, you're going to get 1. So you can cancel out complex numbers like this too. And what is the distributive law of complex numbers? Let's say you have z1 times z2 plus z3. This is equal to z1 times z2 plus z1 times z3. So you can distribute this complex number to the other two. And what is division of complex numbers? z1 over z2 is equal to z1 times 1 over z2. Oh, that's a 3. Now, isn't this pretty obvious? It looks pretty obvious. But what does it actually mean? Like, we know that z1 over z2 is equal to z1 times 1 over z2. But what does that even mean? And now here, we have to learn a topic called a conjugate. Now, if z1 equals a plus bi, then the conjugate of z1, denoted by a bar above the complex numbers, equals a minus bi, which means you just switch the sign in front of the imaginary part of a complex number. Let's say you have z equals 2 plus 3i. then the conjugate of z equals 2 minus 3i. And what this is supposed to represent geometrically is actually its mirror image through the x-axis. But we're going to learn about that in geometry and rotation of complex numbers, the next video. So, if I asked you, what is the conjugate of this? 2 minus 3i. Now I told you, you just switch the sign in front of the imaginary quantity, which gives us the conjugate of z equals 2 plus 3i. Now, what is a modulus, or absolute value of a complex number? So let's say you have z equals a plus bi. What would be the absolute value of z? This is the square root of a squared plus b squared. And how does this actually come? Let's say you have, I'm just going to give an introduction to the argand plane so that we understand how to do this. But this topic isn't until next video. So this is actually the real axis, and this is your imaginary axis in complex numbers. And your complex number is denoted by a point, or in some cases a vector. But let's say you have a line joining it, and you want to measure this distance. So you would have to use the Pythagorean theorem, and you know that this length is a, so this is like a plus bi, a comma b, you could say a comma b. So this length is actually a, and this length is b. You just need to remember that. I'm going to go in depth into this in the next video. So this is your distance from center, or you could say modulus of z. Let's just denote it by like c or something. So c squared equals a squared plus b squared. And that is your typical Pythagorean. So c is equal to the square root of a squared plus b squared. And this is your modulus, or absolute value of z. So you just need to remember that the absolute value or magnitude of a complex number, you could say magnitude, is denoted by these two bars, absolute value function, and this is equal to the square root of a squared plus b squared, where z equals a plus bi. Now let's try a few problems on it. If I give you z equals 2 plus 3i, what would be the modulus of z? And this is under root of 2 squared plus 3 squared. This would be the square root of 4 plus 9, and this is the square root of 13. And you could try prime factorization. You would get the square root of 2 times 2 times 3, which is 2 root 3. Now, we're going back to division of complex numbers. I said z1 over z2 equals z1 times 1 over z2. How does this work? We know that's pretty obvious, but let's say z1 is a plus bi. Now, what do we multiply to a plus bi to make it 1? It's multiplicative inverse. So, let's say you multiply this with x to make it equal to 1. Now, what is x? X is 1 over a plus bi. And actually, the conjugate of a complex number is its multiplicative inverse. So if you want to divide two complex numbers, you have to multiply the conjugate on both the bottom and the top. Let's say I have let's say I have 1 plus 1 plus I divided by 1 minus I. Now we have to multiply by the conjugate of 1 minus I on both the numerator and the denominator. Now we could see on the top it's 1 plus I whole squared. And on the bottom, it's a squared minus b squared. What is that? So this is a minus b times a plus b. And this gives us a squared minus b squared. And here a equals 1 and b equals I. So that would be 1 squared minus I squared. 1 squared is 1 and I squared is negative 1. So 1 minus of negative 1 is 2. So this would be your complex number, and you can still simplify this. This is actually going to cancel out to 2i. Let me just show you how that happens. So this is 1 squared plus I squared plus 2i divided by 2. And 1, and we know I squared is negative 1, so we just cancel these out. And 2 gets canceled out, giving us I. So that's division of complex numbers. And there are some properties of conjugates also. Like, for example, if I told you, what is the conjugate of a conjugate? This is your original complex number, and you could think about it logically too. If I had a plus bi, and I took its conjugate, I would get a minus bi. And I took its conjugate again, I would still get a plus bi. So that's just a property of complex numbers. The second one, complex numbers break, conjugates break upon addition and subtraction of complex numbers too. Like z1 plus or minus z2. And the conjugate of this is equal to z1 conjugate plus or minus z2 conjugate. And the same with division. z1 conjugate or z1 over z2 whole conjugate is equal to z1 conjugate over z2 conjugate. And with multiplication too. z1, z2, z3, let's say up to zn whole conjugate. This would still be z1 conjugate times z2 conjugate times z3 conjugate up to zn conjugate. So these are some basic properties of complex numbers and complex identities. I'm going to be going in detail in the next number. Actually, I have a little concept to explain before we end it off. Z times the conjugate of z equals the modulus of z squared. How? So let's say z equals a plus bi. So z conjugate would be a minus bi. And if we multiply these two, we would get a squared minus abi plus abi minus b squared I squared. These cancel out. A squared minus b squared I squared. And we know this is negative 1, so this becomes plus. And we know modulus of z equals the square root of a squared plus b squared. So the square would be a squared plus b squared. So we proved that z times the conjugate of z equals the square of the absolute values of a complex number. And let's say z is a complex number. Then 1 over z would be 1 over a plus bi. And this is actually equal to a plus bi times a squared plus b squared. And the reason for this is you're going to multiply the conjugate on both the bottom and the top, or the same quantity. And this is a thing to remember. You would actually this is a minus bi and a minus bi times a divided by a squared plus b squared. So how do you get this? A plus bi times a minus bi divided by a minus bi. This is a minus bi divided by a squared plus b squared. And we know this is the conjugate of z, and this is the square of the modulus of z. And we also know that this is the conjugate, and this is z times z conjugate. And these cancel out, giving us 1 over z, which means we basically proved that 1 over z equals z conjugate over the modulus of z. So you need to remember this. Modulus of z squared, actually. So this is a basic introduction to identities and algebra of complex numbers and identities. So I'm going to see you in the next video where I discuss about geometry and rotation of complex numbers, where we discuss about polar coordinates, imaginary quantities on a complex plane, the real axis and imaginary axis as I showed, and the geometric interpretation of all of these things like conjugates and modulus, and plotting complex numbers on graphs and arguments of complex numbers, which we're going